Okay, so I had said that tomorrow in the afternoon I will have office hours, but some of you had asked for if we can do any extra problem-solving hours. So tomorrow, from 12:40 up to 14 in P4. Well, if you bring questions, we can solve your questions. If you don't bring your questions, we can solve some of the example problems in the guidelines. And also before 12:40, I will be in my office. So for those who have some free time in the morning, you can also come and ask questions before the problem-solving hour. Okay? Well, let's say up to 11. Okay, so any questions before we continue about the potential, about anything else that's covered in the exam? Now, you had received the email on Monday that the capacitors is also included in the exam. So what we need to discuss today is connecting capacitors. Dielectrics, and energy stored in capacitors. Any questions you have before we start to, if you remember on Monday, we had already started discussing the capacitors. The idea in calculating the capacitance of whatever configuration you have is that you put the charge then calculate the potential difference it creates. And then you just take the ratio. And this gives you the ratio is just the capacitance. Any questions up to here? Now, the simplest example of a capacitor, we had this parallel plate capacitor, where we imagine that it has some area A, not infinite, but sufficiently large compared to this thickness D, such that we can use the approximate expression for an infinite plate. So if you put some charge, let's say you put a charge Q plus Q on one plate, minus Q on the other plate. Now in this example, putting a charge basically means that you just take some of the charges from one plate and move it to the other side. The whole system is still neutral. There are no extra charges in this system. But you just take some of the charges from one part of the system, move it to the other part of the system, and this creates a potential difference. And now we had already seen that the electric field magnitude was just sigma over epsilon 0. Sigma was the charge per unit area, and that is just the total charge is Q over A times epsilon 0. Q over A is nothing but our sigma. Once we know the electric field, so you see what we did, we put some charge, we calculated the electric field created by that charge. Then the potential difference, since the electric field is just uniform, we don't need to worry about integrals here, it's just the electric field multiplied by this distance, D. This is Q D over A times epsilon 0. Or Q is equal to A times A over D times epsilon 0 times V. And the definition of the capacitance is that the total charge of the system should be equal to the capacitance multiplied by V. So for this system at least, C was epsilon 0 A over D. Now, in real life, we do have these capacitors. But rather than having infinite plates, what we do is you just roll them up. You create cylinders. If you have opened up any circuits, not very modern circuits, but any circuits that have large components in it, you have probably seen circuit elements that look like this. Just a small cylinder with 2 pins. That's the capacitor. So here the idea is you just take these 2 plates, you put them very close to each other, you put something in between so that they don't touch. You don't have a short circuit. You just roll them up so it doesn't take too much of a space. Now, how can we connect them? So basically, there are 2 means of connecting the capacitors. In one of them, one is called the parallel connection. They are connected in parallel. So here the idea is, well, let me just draw it. Well, this is the symbol for a capacitor in a circuit. It's just the parallel plates. And then you connect it to some equipment that provides a potential difference, which is usually the battery. So the battery just provides a constant potential difference. So again, the idea is the same. In calculating the capacitance, whatever your system is, you put some charge. Well, what does it mean? It will mean just moving some charge from here to here. But these are all wires. They are conducting. So the charges, if you put some charge over here, it will not stay here. Some of it will go up. So they will be distributed over this conductor. So at the end of the day, I will have some charge Q1 over here and Q2 over here. Let's say this capacitor has capacitance C1, this one has capacitance C2. Now, the total charge here is Q1 plus Q2. Now, the next question is, what is the potential created by these charges? Well, the potential created, well, you can take between these 2 points if you like. You can take between those 2 points if you like, or between this point and this point. Because since these are conductors, at every point, the potential is the same. There is no potential difference inside the conductor. So let me take this point A and this point B. Well, on one hand, I know that the potential difference, since this is a capacitor, and across this capacitor, if it has a charge Q1, the potential difference should be Q over C1, Q1 over C1. On the other hand, well, this point has the same potential. You see, this point has the same potential as this one. This point has the same potential as this one because they are on the same conductor. The potential difference between these 2 points, if you calculate it across this capacitor, it is just Q1 over C1. But we had already seen that well, let's say, you can also calculate the same potential difference across this capacitor, which will be just Q2 over C2. So this is how the charges will be distributed. If you have a total charge Q, it will be distributed among these 2 capacitors as Q1 and Q2, and Q1 and Q2 are given by these relationships. Now, how do we calculate the capacitance? We know V. This is the potential difference. This is the total charge. Well, take the ratio. The total capacitance of the system is just V over, Q over V, which is Q1 plus Q2 over, well, V, whichever one you like. Let's just choose this one, Q1 over C1. which is equal to C1 times 1 plus Q2 over Q1. Well, this is just, this C1 is now over here. Now I have, if I divide Q1 by Q1, I get 1 plus Q2 over Q1. It is just this term over here. But I know what Q2 over Q1 is. You just look at this relationship over there. So that basically tells me that Q2 over Q1 is C2 over C1. Or the total capacitance is just C1 plus C2. This just tells me that if I have such a system in my circuit, I can basically replace it with a single capacitor that has the capacitance which is the sum of the two capacitances. Well, another way of looking at this is, in fact, let's just imagine these two systems are made up of two parallel plates, and their separation are the same. So their capacitances is just proportional to their area. You see, we had already seen in the parallel plate capacitor, it's proportional to the area if D is the same. But connecting two capacitors by, the shape of the wire is not important. You can just imagine this wire to go from this plate to that plate and from this plate to that plate. You are basically connecting these two plates. But that means you are adding the area. So if you are adding the area, since the capacitance is proportional to the area, adding the area just means adding the capacitances. The total system has a capacitance which is equal to the sum of the capacitances. So that's another way, easy way of remembering whether it's the sum, now we will see, it's the sum of the capacitances or the sum of the 1 over the capacitances. So in this case, we are just summing the areas. Any questions how we drive this? What we use? A couple of things we use over here. One, in a conductor, there's no potential difference. So there's no potential difference over here. So the potential difference across this 2 point, or this 2 point, or these 2 points, they are the same. Second, well, basically, for the calculation of the capacitance, we need to put some charge on my system. Well, if I put some charge, my charge will be distributed over all the points that it can access. So if I put some charge, some of it will be over here, some of it will be over there, Q1 and Q2. And I can calculate this potential difference. You see, if I can calculate the potential difference between A and B. Now, when we talked about the potential differences, we wrote it as an integral of the electric field. Well, and we said that we can evaluate that integral along any path that you like. So I can integrate it along this path. Well, there's no electric field inside the wire, but there's an electric field over here. That will give me a potential difference across this capacitor, which is just Q1 over C1. Sorry, this is C2, this is C1. So I can just calculate the potential difference across this capacitor, which will give me the potential difference as Q1 over C1. Or I can calculate that integral of the electric field along this path. Well, that would just give me the potential difference across that wire. And that would be Q2 over C2 from the definition of the individual capacitances. So we have one relationship already over here. And now we just use the definition of the capacitance. We know the total charge. The total charge is just Q1 plus Q2. The potential difference, well, the potential difference is just VAB. Or V. That's the potential difference across your system. You can use either this one or this one. They are equal. It's up to you which one to use. And then the rest is just to simplify the expression. So we have this capacitance of the system. Well, if we have 3 of them, Well, you can just draw it whichever way you like, by the way. So this is one way of showing the 3 capacitor. Or this is the same thing. These two are the same thing. The only thing I did is I just moved some of the wires. You are allowed to move wires because you are not changing the potential anywhere. Well, there are various ways you can do that. You can just look at this one and remember that the capacitance is proportional to the area. We are connecting the areas by wires. So effectively, we are summing the areas of each one of the capacitors. So the total area or the total capacitance would be just sum of the individual areas or the individual capacitances. Or if you like, you can look at this diagram over here. Here, I already have 2 capacitors. We can replace it by an equivalent capacitor whose capacitance is just the sum of the capacitances of these 2. So this is the same thing as a single capacitor over there, another one over here, and the battery. So this has C1 plus C2, and this has the capacitance C3. What I did was I just replaced the top 2 capacitors with a third capacitor whose capacitance is just the sum of the capacitances of those 2. These 2 circuits are equivalent. Now here I have just the 2 capacitors connected in series. Well, I know that this I can replace by a single capacitor whose capacitance is C1 plus C2 plus C3, whichever way you like. Now, any questions on these? Now let us look at the energy stored. Well, when we were discussing the potential, we said that if there is a potential difference, and if you move a charge from one point to the other point, the energy of the system changes, and the change in the potential energy of the system was just how much charge you have moved across what potential difference. So let's see. Let's take a capacitor. Let's take one charge, let's say from the left plate, 1 electron from the left plate, and let's just assume that we move it to the right plate. How much work do we need to do? What is V? What is Q? Well, there's no charge. Everything is neutral. There's no charge in my capacitor. So I can just move 1 electron without any problem. I don't need to do any work. But once I move 1 electron to this side, now this capacitor is slightly charged, negative. This capacitor is slightly positively charged. So there's a potential difference now. If I move 1 more electron, I need to do some work. If I want to move the third electron, I need to do even more work. And all this work that I have done is actually stored in the system. So that is what I will calculate now. How much energy do we store in a capacitor until we charge it fully? So let's say that during this process, I have already carried many charges. And let's say this is negatively charged. This is positively charged at a given instant. I just started from neutral plates, started moving charges from one plate to the other one, building up the potential difference. At some moment, I look at my system, and my system looks like this. Now, if we carry one more charge, let's say that I have a charge dq, and move it across the capacitor. At this instant, let's say the potential is V. There's a potential difference V, and I move, well, I have been telling I'm moving minus charges here, but it's the same thing as I'm moving positive charges to the other side. So let's say I'm moving a charge dq from this plate to the other plate. Now how much work do I do? There's a potential difference of V, and I'm carrying a charge dq. It's just V times dq. The work done, or the energy stored in the system, as I move this charge from the right to the left, is just V times dq. Let's say that at this instant, the charge of the left plate is, let's say, Q, capital Q. So V is just, what is V in terms of capital Q and the capacitance? Q over C. Now, I just moved this charge from one plate to the other one. How much did Q change, capital Q? Plus dq. So the change in the capital Q is just dq, the very small charge that I moved. So the potential difference, the energy stored, the change in the energy stored of the system as I move this charge, this small charge dq from one plate to the other one, is just Q over C times dq. Now, I just need to sum all of these changes in U as I change the charge in my capacitor. So that sum is nothing but the integral. So at the beginning of the process, what is the potential energy stored in my system? At the beginning, my capacitor is neutral. There is no charge in my capacitor. 0. Initially, there is no energy. Let's say finally, let's just denote the final energy as U. What is the initial charge of my system? Initially, it was neutral. So what's the charge? 0. Let's say finally, it's capital Q. Or let me just put primes for the time being. Well, the left integral is just U. U prime is equal to 1 over 2c q squared, q changing from 0 to q prime. Or let's say U is equal to 1 over 2c q squared. So if you know the total charge in your capacitor, then you can calculate the total energy stored in your capacitor. Or usually we don't know the charge stored in the capacitor, but we know the voltage of the battery. So we would rather express everything in terms of the voltage, but Q is nothing but C times V. So this is 1 over 2 C times V squared. So this is the energy stored in a capacitor. Well, let's calculate the parallel plate capacitors. Now, capacitors in series, in parallel. What is the total energy stored? Well, some of the energy is stored in this capacitor. Which is the total energy 1/2 C1. What is the potential difference across this capacitor? It's just V. C1 times V squared plus 1/2. The energy stored in the other capacitor will be C2 times V squared, or 1/2 C1 plus C2 times V squared. You see, before we had claimed that if you have such two capacitors connected in parallel, to get the same effect, you can replace this system by a single capacitor with capacitance equal to C1 plus C2. Well, at least in the case of the energy, we have explicitly checked that. This is the energy stored in the first capacitor. This is the energy stored in the second capacitor. This is the energy that would be stored in a capacitor whose total capacitance is C1 plus C2, and the potential difference is V. Now, let's also look at the other way of calculating the capacitance, connecting the capacitors. You see, we have two capacitors, but this time we don't connect the corresponding plates together, but we connect them like this. We connect one plate of one capacitor to the battery and one plate of the other capacitor to the battery. You see, in the previous case, in this case, we connected all the plates of the capacitors to the battery. But in this case, in the series connection, one plate of each capacitor is connected to the battery. The other plates are connected to each other. So now we need to calculate the total capacitance of this one. So let's see. Again, the strategy is always the same. First, let's put some charge on my system. Now, how do we put this charge? Well, we take some charge from one region, one end of my system. I just extract charge from one end and put it on the other end. So at the end of the day, I will have, for example, this capacitor charge plus Q and this capacitor charge minus Q. But you see, if I have a plus Q charge in this plate, it will attract the minus charges. So this plate will be negatively charged. And the amount of charge that will come to that plate is exactly minus Q. And this plate is negatively charged, so it will repel the electrons, and it will be positively charged, and it will also be plus Q. So this is this is an isolated conductor as a whole. You see, it doesn't connect to anything else. And this isolated conductor it was neutral before, it is neutral now. So the total charge of that part is still 0. Okay, so now we managed to put the charges. Let's say that this has capacitance C1, this has capacitance C2. Let's say this point is A, this point is B, and this point is C. VHC, the total potential difference between those 2 points, which is just V. That is the potential difference created when we charge the capacitors. So that is our V. And this is equal to VAB plus VBC. Now why? You see, the potential difference was the integral from A to C of the electric field. But the integral from A to C, I can just take it from A to B first, and then from B to C. And that would give me the potential difference between A to B, and then potential difference between B to C. So you see, I just divide the integral from A to C into two parts, from A to B and B to A. The integral from A to B is nothing but the potential difference between the points A and B. And the integral from B to C, B to C is nothing but the potential difference between the points B and C. So it's this relation over there. Now, what is VAB? There's a capacitor over there. I'm going over the capacitor. What is the potential difference across the capacitor? Q over C. And VBC, no, this is Q over C1, and VBC is Q over C2. So the total potential difference across my system is Q over C1 plus Q over C2, or Q times 1 over C1 plus 1 over C2. But you see, the potential difference and charge are related by 1 over C. So on one hand, we have V is equal to Q times this number. On the other hand, V has to be equal to Q over the capacitance of my system. So this has to be the capacitance of my system. Now, most of the time when you are connecting capacitors, not necessarily one of them, many of them, you will have these two types of connections. Either the corresponding side, all the surfaces of your capacitor are connected to the battery, or some of them are connected to the battery, other ones are connected among themselves. That would be the series connection. Now, for example, a simple example would be, let's see, let's say C1, let's assume that they are all identical. Now we can ask, what is the total energy stored? Well, if you want to calculate the total energy stored in the system, what you can do is, well, you can just go and calculate the charges of each one of those capacitors. And then once you know the charge of each one of those capacitors, then you know the energy stored in each one of the capacitors, and then sum them up. Or what you can do is you can just first calculate the equivalent capacitance of the system. And this system, well, on one hand here we have a series connection. So this system is in fact the same as two capacitors in parallel. This is C, this is C1. Now C1 is what I use instead of these two capacitors. Now those two capacitors are connected in series, So their total capacitance, the inverse of it is 1 over C, the sum of the inverses. 2 over C, or C1 is equal to C over 2. But now I have two capacitors connected in parallel. I can just say that, okay, this is the same as a single battery and a single capacitor, with the capacitance equal to the sum. I have one capacitor with capacitance C, a second capacitor with capacitance C over 2. The total capacitance is just the sum of them, which is 3 over 2C. Now I know the equivalent capacitance of my system. I know the potential difference across the ends. I can just write down the energy. Any questions? And finally, dielectrics. Now, we will solve more examples in the second hour. So you see, when I was mentioning about the capacitors, I said that, okay, we take these two parallel plates, put something in between. If you put something in between, and then they will not short, they will not touch each other, so we can just, before going to this, before starting dielectrics, sorry, let's look at this problem, this result. You see, when we are connecting those two surfaces, those two plates together by a wire, well, I mean, you can actually bring those surfaces together. I mean, this wire just tells me that this point and this point, they basically have the same potential. This plate and this plate, they should have the same potential. So let's just imagine that we don't put any wire, but we just bring those two surfaces actually touch each other. So we have this system is actually the same thing as this one. Let's say this is D1. This is D2. Let's just, again, for simplicity, assume they all have the same area. This is D1. This is D2. This one and this one basically have the same potential difference between this point and that point. Because by connecting these 2 points by a wire, we are forcing this point and this point to have the same potential. So the potential difference between this point and this point is actually the potential difference created across this wire plus the potential difference created across this wire, across this capacitor. Well, it's the same over here. Now, this plate is neutral because if this is minus Q charge, this was plus Q charge. This plate is neutral. There's no charge distribution. But that means basically I can remove it. It has practically no effect on my system. So this is the same thing as this system, with the separation of the areas, just the sum. Now remember, 1 over C, for a parallel plate capacitor, C was epsilon 0 A over D. 1 over C is epsilon 0 over A times D. It's just in the case of the series connection, now parallel connection, we were summing the areas. Now here in the case of the series connection, we are summing the Ds to change the capacitance of the system. So the fact that D plus 1, D1 plus D2 is actually equal to D1 plus D2. Just multiply both sides by epsilon 0 over A. No, A over epsilon, sorry. Here I made a mistake. 1 over C is A over epsilon 0. If we just multiply both sides by A over epsilon 0, this is the capacitance of the combined system, equivalent 1 over the capacitance. This is 1 over C1. Sorry, I made several mistakes. This is epsilon 0 over A. 1 over epsilon 0 times A. Okay. So when we connect them in series, we are basically adding their separation. When we are connecting them in parallel, we are basically adding the areas, because we are connecting the areas together by wires. Here we are connecting the whole separation by a wire. Any questions about capacitors in general? Yeah, I will not rush the dielectrics. I mean, you can leave it for the next hour. Maybe let's look at one of the examples in the book. Now, in one of the questions, this is example 2410. So you have a parallel plate capacitor, plates having an area A, and then their separation is X, and they are both connected to a battery, which provides a voltage difference V. Then you exert a force, and you move one of those plates. This one is fixed. The other one is moved to a distance 3x, still connected to a battery V, to the battery. How much work do you do? How much does the energy of the battery changes? Sorry, how much the energy of the capacitor changes, and how much work do you do? Well, let's start with the change in the energy stored in the capacitors. Well, the energy stored in a capacitor is just 1 over, let's say initially the capacitance is C. Finally, the capacitance will be, what is the final capacitance in terms of C? C over 3. So this is 1 over 2, the final capacitance times the final voltage squared. This is the final energy stored in the capacitor, minus 1 over 2, the initial capacitance times the initial potential difference squared. This is the initial energy stored in the capacitor. Well, the final capacitance is C over 3. And what is the final voltage? V. Minus 1 over 2 C V squared. This is equal to 1 over 6 minus 1 over 2 times C V squared minus 1 over 3 C V squared. This is delta U. This is how much the internal energy changes. let's see how much work do you do. Now let's assume that at a given instant, let's say, they have a, let's say, a charge sigma, a surface charge density sigma, plus sigma on one side, minus sigma on the other side. So how much force, what is the minimum force that you need to exert to be able to separate these plates? So this is the question. We have a parallel plates. There is a surface charge density sigma, plus sigma on one side, minus sigma on the other side. How much force do they exert on each other? We know that the electric field inside was sigma over epsilon 0. And let's say that the total area is just Q. No, total area is A. So that the total charge is sigma times A. So how much force do they exert on each other? So what was the relation between the electric field and the force? Q times E. So to calculate the force acting on this one, we need to calculate the total charge. Well, the total charge is minus Q. And what is the electric field created by the other plate at the position of this plate? You see, this sigma over epsilon 0 is the electric field created by both of these plates. But the electric field created by this plate doesn't exert any force on itself. So it's only the electric field created by this one that is exerting the force on this one. And the electric field created by this one is just half of this one. So the force acting on this, the attractive force between these two plates is actually sigma over 2 epsilon 0 times Q, or Q squared over 2 epsilon 0 A. This is the force that you need to exert. This is the force of attraction, so if you want to separate them, you have to exert at least this much force. Now, the work done is just the integral of the force, dF times, let's say, dL. So you are, this is the external force. You are exerting this force, external force. Now let's see. This is equal to, well, the external force and dL, they are both pointing on the same direction. So it's just F times dL. And the force, we just said that is Q squared over 2 epsilon 0 A times dL. No, it's not a minus. Why should I? Well, one of them is fixed. One plate is fixed. I'm moving the other plate. So this is, I mean, the other force, you have to, of course, hold the other plate, but it's not moving. So it's not doing any work. So it's only this plate is moving with zero acceleration. And the force I have to exert is this much. I'm just multiplying it with my displacement. Why? Because the force that this feels will be due to the electric field created by the other plate. And this plate on its own creates an electric field sigma over 2 epsilon 0. Sure. Okay, so let's continue. Now, what depends on their separation in this expression? Does A depend on the separation of the plates? Epsilon 0, 2, Q. Q depends on the separation. Because you see, what do we know about Q? Q is C times V. V is fixed by the battery. So unless you change the battery, V doesn't change. V doesn't change, 2 doesn't change, epsilon 0 doesn't change, A doesn't change, but C does change. C is inversely proportional to the separation. This is equal to, well, V squared over 2 epsilon 0 A. C was epsilon 0 times A times 1 over the separation. Now I have the C squared, dl. dl is my discrete step while I'm moving the plate. Every time I move, d changes by dl. So that dl is actually dd, the change in d. So let me simplify this epsilon 0 a. So this is 1 over 2 epsilon 0 a v squared integral of 1 over d squared. What is the minimum value of d, the first value? X up to 3x. So this is equal to 1 over 2 epsilon 0 a v squared, 1 over d as d goes from x to 3x. 1 over 2 epsilon 0 a v squared times 1 over 3x minus 1 over x. This is minus 1 over 2 epsilon 0 a v squared over x times 2 over 3 or 1 over 3. This is 2 over 3 times x. The work done is minus 1 over 3 c v squared. Oh, the integral also has a minus sign, yes. So here there is a minus sign. There is a minus sign over here, so this is plus. So this is minus. So this is plus. Because c is epsilon 0 a over x. Because we allow the Q to change. The battery fixes V. In order to fix the potential difference, it changes the charges in the capacitor. Well, let's just compare the potential difference. The change in the potential energy of the system is minus 1/3 CV squared. The work that we do is plus 1/3 CV squared. You see, let's see. Let's assume 2 charges. Okay, so if I want to calculate the force that this charge feels, what do? I first calculate the electric field created by this charge, only this charge, multiply it with the charge over here. So now I have 2 plates. To calculate the force acting on this one, I need to do the same thing. I need to calculate the electric field created by the other charges in my system. So this is one of my plate. So I have to first find the electric field created by this single plate. Just one of them. And the electric field created by an infinite single plate was just sigma over 2 epsilon 0, not sigma over epsilon 0. sigma over epsilon 0. You see here, sigma over epsilon 0 is the electric field created by this plate plus the electric field created by this plate. It's the sum of the two electric fields. That gives us sigma over epsilon 0. But the force that this plate will feel will be only due to the electric field created by the other plate. That is why I'm not taking the half. I'm only calculating the electric field created by this plate, which happens to be half of that one. No. You see, this is the work that we have to do. If this was the whole story, the work that we have done should be equal to the change in the potential energy. But it is not, because there is the battery. Battery also does the work. So you see, if you calculate, let's just assume you take a mass, you raise it. Did I do positive work or negative work? I did a positive work. I am applying a force in the upward direction. It is displaced in the upward direction. I am doing positive work. Now, did the change in the potential energy, is it positive or negative? Positive. You see, in a conserved system, the work that you do is stored in the potential energy. They are equal. The change in the potential energy is equal to the work done by the external forces, not the opposite sign. Exactly equal to. Here, they are not equal to, because basically we didn't take into account all the work done in the system. The battery is also doing work that we didn't calculate. So that is why in this example, the external work that is done is not equal to the change in the potential energy. Well, the minus just turns out to be a coincidence. I mean, they seem to have the same magnitude, but I can say that it's just a coincidence, let's say. Okay, let's give a break. And in the next hour, we will look at the dielectrics and solve some more examples.